Good day. Today this is part 4 of presentation on the Kakutani for Neumann transformation, and this last part will be about the Chacon transformation. We have seen a process of constructing transformations called cutting and stacking that yields what in general are called the rank 1 transformations, important class of measure preserving. Our first example was the von Neumann-Kakutani transformation, also called the dyadic odometer or the dyadic adding machine. And we saw that it was constructed inductively by giving a sequence of columns. And we proved that this transformation is ergodic. Square, the second iterate, is not ergodic. In part 3, we reviewed the Kakutani polynomial transformation, or odometer. We call it T in part 3, and we introduced new transformation, Chacon transformation. In this part, we will prove two important properties of the Chacon transformation, namely that it is a weakly mixing transformation, which the Kakutani polynomial transformation is not, but it is not a mixing. So it's an interesting example of transformation that is weakly mixing and not mixing. What we will do is we will start by reviewing the construction of the Chacon transformation. So here's the Chacon transformation. This time we are going to call it T, Chacon transformation T. In part 3 we called it S because our Kakutani polynomial was a T, but here we will only have one transformation, the Chacon transformation, that we will call it T. This transformation is also constructed by cutting and stacking, and we will recall the construction. So there's the base step C0, which is the column C0, which is in this case consists of the interval 0 2/3. And now what we're going to do is give the inductive step. Given column Cn, assuming that Cn has been constructed, we will show how to construct Cn plus 1. Now, Cn consists of Hn levels or intervals. We call them levels. They are all subintervals of the unit interval, all of the same length. Here it is. This is Chn. The height of Cn is Hn. We're going to, because of the construction, this is a level, I'm going to go up to here. That was Hn. Okay, so this is an arbitrary level that we will call it I. In a moment, we'll give it a name. This is the base of the column. That's the top of the column. It has Hn levels. So what do we do for the inductive step? To obtain Cn plus 1 from Cn, what we do is cut each level into 3 pieces. So we subdivide this equally into 3 sublevels. This is also subdivided into 3 sublevels. This is subdivided into 3 sublevels. Then we stack the right subcolumns on top, but before that we add a new sublevel here that we call a spacer. You may have recalled the name of this is a spacer. And this is a new level that is obtained from the part of the unit interval that has not been used yet. Okay. For example, in C0, when we want to construct C1, we would cut that into 3 pieces, and we would take an interval starting at 2/3 of length 2/9. Okay. We take that, going back here to the construction, we put the spacer here, and then we stack from left to right. So what that means is this sublevel here is sent to the bottom of the middle subcolumn. This goes into the spacer, and then this spacer here is sent to the last sublevel of the bottom of there. So this will create a column of Hcn plus 1 of height Hn plus 1, which will be 3 times Hn plus 1 because of the space. So the number of levels of Hn. So for each n, we have defined a column Cn, Given a column, we know that the way the transformation T acts is sends a point to the point above it. Since in the limit this will cover all the points in the unit interval, we have defined a transformation on the unit interval. The basic properties that we originally asked proof for the Neumann Kakutani transformation, which is that it is measure preserving and ergodic, are also true in this case. Measure preserving and ergodic. So this transformation is also measure preserving and ergodic, and the argument we gave before holds in this case. What we're going to do now is prove two new properties, and the first one is that T is weakly mixing. So this is the new part. T is weakly mixing. This is a very important property that implies ergodicity, but is not implied by ergodicity. There are several equivalent definitions of weakly mixing. We will use one called continuous spectrum. We will not go into the details of that. The motivation for that is the interpretation that this has in terms of its spectral measure that we're not going to cover. So the definition of weakly mixing that we will use is that if f is an L2 function, so that is a square interval function, and f is an eigenvalue for t, that means f or composed with t equals lambda f, AE. So this means f of t of x equals lambda f of x for almost all x's. Then it has to be the case that lambda is 1. Lambda that satisfying this condition is called an eigenvalue for t, and this is saying that the only eigenvalues of t, the only eigenvalue of t is 1. This is an interesting and important characterization of weakly mixing. You may try to show that for the Kakutani polynomial transformation, there are lambdas that are not equal to 1 that satisfies that equation. So you're invited to show that for the Kakutani polynomial transformations, there are a lot of values of lambda that satisfy that equation, which are not equal to 1. Well, going back to this property now. So there's only one lambda, lambda equal to 1 is the only eigenvalue. Now, there are a couple of things to remark about this property. The first one is that f is in L2, and since we are in a finite measurable space, we know that f is in L1, and we can put absolute values on both sides and integrate. The absolute value of f comes out, or the modulus of f of lambda comes out, excuse me, not f, but absolute value of lambda comes out, because it's a constant, comes out to the integral. And we'll make a remark here, is that, let's note, that one can show that the absolute value of lambda is 1. Here, incidentally, I would like to remark that the functions f, the L2 space is a complex valued function, so we are considering complex valued functions, and lambda is a complex number. And an eigenvalue of a finite measurable space transformation must satisfy the property that its modulus is 1, the absolute value is 1. Because of that, we can assume that f is of constant modulus. It follows that it has to have constant modulus because t is ergodic. Since t is ergodic, one can verify that from the fact that this has absolute value, the modulus of f is constant, and we can assume this modulus is 1, just for definiteness. So we can just consider complex valued functions whose values are in the unit circle. All right. So that is the definition of weakly mixing, and what we want to do now is prove that this transformation, the Chacon transformation, satisfies this property. All right. Now, first, because f is measurable, given epsilon, one can observe that there is a constant c such that the measure of the x's such that in absolute value f of x is epsilon close to c is positive. Okay? This is something that you're all invited to prove. It's a consequence, for example, if you're familiar with points of Lebesgue density, so it would be a consequence of that, but one can give a direct proof of this by looking at all the x's which are epsilon close to the rationals and take the union over all n's or all rationals. That set has to be a set of full measure, and therefore must exist at least one that has positive measure. So let's call this set here A. That A. All right? So that's a set of positive measure. Since the levels generate, it must be the case that there's a level that is very full of A. So there has to exist a level I. There's a level, just here. There's a level I in some column, and because of we already have this picture, let's assume it's in column Cn. In Cn, for some n, there has to exist an n, such that the measure of A intersected that level I is bigger than, we will see that it's enough to take 6 measure of I. Okay? But intuitively, it's a good idea to think about it as very full. And we're going to draw that, let's draw that here, the set A in the level I. So this is a level I. It's a level I in some column, which we're saying Cn. And then there is A here that is occupying a lot of I. Okay, we see a lot of A here. We see a lot of A. Okay? So it must cover more than half of this third, more than half of this third, and more than half of that third. Okay? So therefore, it follows that there has to be a point, I can put it, there has to be a point x, so that is in A. So there's a point x in A, so that when we move that, it comes back to A. So if you move this point up, you will see by hn, it comes back to A. So that's t to the hn of x is in A. And if we continue again, we will continue by another hn plus 1. So t to the 2hn plus 1 of x is in A. Okay? So there has to be such a point because there's a lot of A in this interval. And the plus 1 we will see is crucial, and that's the role of the spacer. There's a bump that the spacers create. So now, since x is in A, we know that f of x is very close to C. Since t of hn of x is in A, we know that f of thn of x is close to C, but because of the property of eigenvalues, and since f is an eigenfunction, this tells us, this second part tells us that lambda to the hn f of x minus c is less than epsilon. Okay? And this one is in A, so that will tell us that lambda to the 2hn plus 1 minus c f of x here is less than epsilon. Okay? And then this part, maybe we'll just write it here. This is telling us that f of x minus c is less than epsilon. So we have these three conditions. So let's think about intuitive. So we'll say f of x is essentially c. Since this is essentially c, that means that we can, lambda to the hn has to be essentially 1. And since this is essentially c and f of x is c, you cancel that, and lambda to the 2hn has to be essentially 1. So in other words, from there you can get the inequality that lambda to the hn minus 1 is less than 2 epsilon, and lambda to the 2hn plus 1 minus 1 is less than 2 epsilon. Okay. Now, since you have lambda to the hn close to 1, lambda to the 2hn will also be close to 1, maybe 4 epsilon there. And since lambda to the 2hn is close to 1, and lambda to the 2hn plus 1 is also close to 1, this will imply that lambda will be close to 1, maybe with a 5 epsilon. And that gives us that lambda is 1. Therefore, lambda is 1. And then it's the proof. It's a very interesting argument that you can see is very robust in the sense that we can do the same argument when we have the construction infinitely often. It's enough to know that you see this picture infinitely often. You can think about that. That question is an interesting question to think about. So what I've done is completed the proof that T is a weakly mixing transformation. It satisfies this property that we said is continuous spectrum, and that property implies, in particular, is equivalent that T cross T, the Cartesian T with itself, is ergodic, and that is an interesting equivalent characterization of weakly mixing, that the product is ergodic. Okay. And that's a property that the Kakutani polynomial transformation or odometer does not satisfy. Okay. So we have seen an important example of weakly mixing transformation. Let us now just finish the last part, which we claim that it is indeed not mixing. Okay? So we're going to pick a level that is going to, it will enough to assume that the level has length less than a half. So very quickly, all the levels here have length less than a half, you know, the next, in C1, C2 already. So let's assume you have some Cn, and we look at a particular level, and now we're going to ask, you fix the level, might as well call it I, we already have it in this picture. And what we're going to ask is what happens under iteration by Hn. Let's just apply Hn to that level. See that this part here, this third, the left third, under Hn comes back over here. And I will use I'm going to use this symbol to mean that it comes back, that this comes back here under Hn. Okay. And then under this part, under Hn doesn't come back because it gets delayed by that. So this part here comes back here. You have that picture. Okay. But if you continue now, so we've seen where that goes under Hn and where this goes under Hn. Now let's see where this goes under Hn. So you have to cut it into thirds, and you have to think of this in Cn plus 1, where this is a single level of Cn plus 1. So its leftmost third is going to go here. And the middle third will get delayed by the spacer that will be put here, and it will go here. And we see that there's an interesting pattern, sort of fractal, like this pattern here that gets repeated over here, infinitely often. You can see that under Hn, and we will see that, and T to the Hn of I is in fact completely, half of it is in this part, and the other half is in the lower part. T to the Hn of I is, half of it is contained in I, and the other half is one level below I. Okay. There is one claim I'm going to make here where you are asked to verify this on your own, which is the following, that because of the construction of the transformation, this is true for fixed I, not only for n, but it's true for all k greater than or equal than n. Let's just start thinking about Hn, but in fact, it follows as true for all k greater than or equal than n. One can argue that by induction. You look at Cn plus 1 and see that the same thing, each I is doing the same thing. Okay? So the claim that we have made, let me write it here, maybe with space. We have made the claim that if we look at the measure of t to the hn of I, and you intersect it with I, that is at least a half. In fact, one can argue this, one can prove it's a half, but at least a half from this, the measure of I. Okay. So that argument has followed from here. Look at an interval I, and you see that this is true for any interval I. In fact, the particular nature of I was not necessary. This third comes back here. This third goes one level below, but then here, there will be that ninth comes back there, and the other ninth comes back here, and you add up, half of the measure will come back in this pattern, and the other half of the measure will come back here, or level below. Okay. So you can say more, but you can say more. You can say what happens when you intersect it with I, and you can say what happens when you intersect it with t minus 1 over I, one level. But in this case, for our argument right now, it's enough to know what happens with I. And then next things I said is, in fact, that's true for not just hn, but hk. This n could be made into a k, for any k greater or equal than n. Okay. Now, if t were mixing, this would have to converge, and let me do it here. It would have to converge to the measure of I times the measure of I. If it were mixing, it would have to converge to the product of the measures. That is the definition of mixing, a mixing transformation. But what we have done is we have found a sequence along which this is bounded below by a half measure of I. And since the measure of I is less than a half, there's no way that this can converge. So here we'll write no. There's no way that this can converge. This doesn't happen. It doesn't converge to the measure of I times the measure of I. Therefore, it is not mixing. That finishes the proof that it's not mixing. Let me say a few words about this transformation, and first about this proof. This proof yields a lot of interesting results. Maybe say it's very robust. You can change it in several ways. For example, you can also say that under that sequence, t to the hn of I is just between I and t to the minus 1 of I. So it cannot intersect the level below under that sequence. And mixing, it would have to intersect other sets. Okay, so that's another proof that it is not mixing. Yeah. This property here is called partial rigidity. And I'll leave you with a question that is very interesting. You can actually find a sequence along which you can do better than a half. You can find a sequence along which the measure of every level comes back in at least 2/3 measure of the level. So that's a challenge question to find that. Okay. So now to review what we have done, and this is the last part of our presentations, part 4. We started in part 1 with a specific pole, the Kakutani Neumann transformation, also called the odometer transformation, or the adding machine transformation, or the dyadic adding machine, or the dyadic odometer. We defined that transformation using a construction called cutting and stacking, which is an inductive process, and we prove using that transformation is measure preserving and ergodic. So that process called cutting and stacking is the way to define a large class of transformations called rank 1. We also prove any polynomial transformation does not satisfy the property that its square is ergodic. And you are asked to verify that if t cross t is ergodic, it has to follow that all the powers that are non-zero have to be ergodic. Then in part 3, we recall the Kakutani polynomial transformation, but then we introduced a new transformation called the Chacon transformation. And we prove with its construction that is simple to the Kakutani polynomial transformation in the sense that it's also a construction by cutting and stacking, but in this case we use this new idea of a spacer. Using that spacer, in this last part, we of its fundamental properties. The first one, that it is weakly mixing, and then that mixing. And with this, we end our fourth part of the presentation. Thank you.